apparently it seems that 90% of you already know Kamil, so there's really no sense in me having to introduce him again. But did you know that he was in a band? Asphalt Liquors. And I'll tell you why, because he's the one who actually introduced me to the concept of asphalt tasting beer. Think about that for a second. Who had the flash of genius when it came to that idea? No idea. But anyway, Kamil.
Hello everyone, I'm Kamil Witecki. Today we'll be talking about asynchronous code that will be readable. That is a very important asset for us, but before we start, let's thank René for introducing me and other people and all the guys who made it happen, the technical guys. You do not see them, but they do a great job during the whole conference. So, asynchronous code, readable one. Our session, it will last about an hour. We'll have a special time for Q&A at the end. So, should you have a question, keep it with you. If I will answer it during the presentation, then profit. If not, wait for it. We will have time for it. No worries. So, today, this very day during the code dive, I want you to remember from this presentation exactly 3 things. We'll discuss 3 different approaches. There will be callbacks, there will be promises, and coroutines. And as you can see here, callbacks, these are very crude tools, and you shouldn't be using them. Yes, it's easy to grab some stone from the dirt, but is it really useful? I don't think so. Then we have promises. These tools have way better handling, so finally somebody had an idea to make it an actual tool and have a hole in it. They provide you a handling, you can have a control over your code, you can structure it well, but still they are lacking. What we really need are coroutines. Shiny, new, very good solution. So, you will ask yourself, why are we going to discuss that? Because things are different in the world. Of course, there were people who used that, but we evolved. And so we evolved, our code should too. So from the simple tools, prehistoric ones, through better tools, we'll finally reach the best possible solution. Why is it important? Because readability of the code is something we cannot really measure, but it matters. It matters the most for the people who read the code. When you write the code, you are in your personal space, you have some problem to solve. Of course, there is always somebody nagging you, deliver it faster, why you are spending so much time on writing tests. Yes, there is pressure, we all get that. But when you write the code, you write what you have on your mind, you can focus on it, and you provide, and you forget about it. But there is one thing far worse than creating code. Imagine right now that you swapped places with somebody who will maintain your code after a year. I can hear you sobbing back there. That's not a problem, it's okay. That's scary vision. It's fine, it's fine. Okay, let's continue. Writing is easy, but maintaining code is like walk through the temple of doom. Actually, life of Indiana Jones was simple. He went to the temple, there were some traps, pitfalls, but he took what he needed, the treasure, and he went back. When you are dealing with maintenance code written by somebody else 1 year ago, maintained by a few different persons, there are pitfalls everywhere. You can trust nothing. If that variable is named sin, is it really a sinus of something? Or maybe it's input stream? I don't know. People have different ideas. They provide you variables like x, x2, and x3, all with different type. So we need to take care about readability of the code. I think you already get the point. So this is a very simple example. It is simplistic. So we have a simple function, but if you read this function, do you know what it does? Look at it. It's not obvious. Even it tells you that it counts some zeros. What it does? we can write it differently. If you write it this way, actually the code itself tells you what it does. It counts from beginning of the container to the end of the container the number of null pointers. Simple as that. So we'll see how to write the code, asynchronous code, that will be more like the second snippet and less like the first one. After this presentation, I want you to promise me one thing. You will refuse to ever work with an asynchronous code in a programming language that doesn't support coroutines. And if you are still here with me, I believe you can keep that promise. And that guy will be fired by his manager. So what is the synchronous code, asynchronous code? I think most of us here know what synchronous code is. This is basically the code that we are writing since the 1950s. Of course, I wasn't there back then, but that's simple code. When I am asking operating system to provide me data from file system, I am issuing an operation, I am starting it, my program stops execution, and after some time, kernel gets the data, passes it to my application gets the result, and only then my code continues. It's very easy, very simple, not very effective, because the application is idling during that time. So if we want to improve latency of our solutions, we must think how to schedule additional operations while we are working with other resources, with remote servers, with file systems, and so on. And that's why we have asynchronous solutions. In case of asynchronous code, when I start an operation, for example, reading a file from file system, I am starting it, but my code continues to execute. I am not receiving the result immediately. I won't get it. I need to execute all other code, and the result will only be given to my application in some kind of completion token. You will not get it as a result of your call, but it will get enqueued somewhere in your application, and you will need to handle it separately. And we will now see how we can handle these asynchronous completion tokens. During the presentation, we will be looking at 3 different cases. The first case is a simple conversation between 2 parties. So, for example, having few different functions, processing some parameters, and they return values. In case of this simple mathematical expression, if we want to express it in synchronous code, it is as simple as this one. Miraculously familiar and similar. What sorcery this is. Of course, we can rewrite it in this way, so is it better or not? We won't argue, it's basically the same thing. In that case, we are actually discussing this situation. We have 2 different entities, Alice and Bob. Alice is asking about something, Bob responds. Then Alice is asking back, because maybe she learned something from Bob. And I hope they will finally set up the date between them at the end of this conversation. The next case will be about flow control, because life is not that simple that we have only conversation between 2 parties. Sometimes we have, for example, 2 different operations. We need to wait for them, join the results, and then process the joint result. We'll look at the simple example where we are reading 2 different files, and we want to compare the content of them. How we do it is not that important. It's important how we deal with that joining of asynchronous operation results. And last, but not least, example is dealing with this guy. It's a bug. Who likes bugs in the software? Raise your hand. I see there are few people with very weird sense of humor. Thank you, guys. I will remember that. We will have something to talk later on during the after party. So we'll be looking how errors will be manifested by the programming language, but by the framework, when they happen in the code, and how much information we can get from it, and how it helps us with debugging the software itself. So, are you ready?
Yeah.
Louder! Yes, very well. Let's start then. First approach will be callbacks. These are the tools that are usually embedded in APIs of different frameworks and solutions. For example, Boost ASIO, Loovit, Node.js, they are all built around callbacks. Any other solutions are actually wrappers or some additional shims built on top of callbacks. What callback is, I think it's pretty simple, and you actually used callbacks in your life. Maybe you are not aware of it, but surely you did. Callback itself is just a simple function that is supposed to take some parameters once the operation itself completes. So for example, when we look at this C++ example, we have a read operation. We schedule it. We are asking somebody to do that read for us. And we provide the callback that will be fired, that will be executed once the results of the operation are available. We do the very same for Lua and JavaScript. And this is the very last example of code in C++ during this presentation. Unfortunately, our beloved standard committee didn't yet proceed with the Coroutines example. But thanks to that, when they actually do that, you will be ready. So, this is the pitfall we can get into when we are using callbacks. This is our conversation example. It's called callback hell. You can see there is something going on, but there is a lot of boilerplate. And this code actually does nothing. It just calls some functions, checks for errors, and there is nothing processed. It's basically doing nothing. It's just boilerplate. Do you like this kind of code? Let's see, maybe not. Maybe we can do better still with callbacks. We can rewrite it this way. Is it better? Maybe less nested, but it's really better. With that code, at least I can follow more or less what the structure of code is and what the business logic is. I can tell that there is some A, then it will somehow call B, then it will somehow call C, then D, then E. Of course, it's not that easy to track if there is more code in between, but it is more or less the same. You know, business logic and code structure more or less follow each other. And here we have lost that, because A calls some handle results of A, but this is defined here. And this then calls some B, but if we go other way around, there is some handle of result of C. Where is it called? Here. So is it really good? Do you like this kind of code? One or the another? If you like it, raise your hand. There is one guy at the very last row, and probably he didn't hear the question very well. Did you? Okay, I believe you. There are different tastes, so I'm not judging. But in my opinion, I agree with most of you. This code looks like this. It's a bowl of spaghetti. So, of course, I can tell there is some code, there is spaghetti. There are spaghetti threads, there is a lot of them. But if I want to track any of them, is it really simple? Where it starts, where it ends, what's that? And obviously, in normal spaghetti, it wouldn't be that clean. There would be some kind of sauce, so additional code, error handling, and so on. You are never going to track one spaghetti thread without getting dirty all over. Then the next case, debugging. You might remember that I told you there will be 3 different cases: conversation, flow control, and debugging. Conversation was first. The third one, the last one, was debugging. So what happened with the flow control? You cannot do flow control with callbacks, really. Okay, you can do that. You can handcraft everything, but it's not a solution. Callbacks provide you no way to do it in some standardized way. Of course, everybody can have one's own solution, but every programmer will do it differently. And as many programmers, as many solutions. Does it help readability? Let's think about it. Does it help? Anybody thinks it helps? Raise your hand. Not even the guy in the last row. I thought so. So So we'll skip that example. There is no point in checking that because there is basically no solution. And when it comes to debugging, let's see this very simple example. We are checking 2 files in the file system, and then we are checking the third one. Obviously, function is not a file, or it doesn't name any. So it's an obvious bug, obvious error in our code. Let's see how Node.js, the best-in-class, the state-of-the-art solution, handles this one. The laughs were too early. This one is handled quite well. The error is in the line 4. Apparently, the line number 4 is the one where we did the error. So from this information, I can actually tell what is wrong with the code, and I can fix it. So far, so good. I like this. Do you like this? Do you like this? Anybody like this? Yes, I agree with you. There are not many of you, but this is good enough. What happens now? Obviously, if our code grows and we are getting more and more convenience wrapper, like for example, something to write configuration file and maybe sanitize it or whatever, we'll get this kind of convenience wrappers. What happens if I provide wrong data to the convenience wrapper? Remember, the actual bug, line number 8, the unguilty line number 4. There is no error in this particular line. Error is here. I have provided as a name of the file and as the continuation function something that is not a function. It will go from here to here. It cannot go this way. The bug is already here. Let's see. What is that? What is that? Really? Come on. Line number 4. It's not guilty. It's just an auxiliary helper. It's a wrapper. There is no bug there. The bug was in number 8. Anybody sees number 8 here in this call stack? Anybody does? I don't. Yes, of course, but it is not related to test.js. So with this kind of information, we are doomed. Imagine you have a very small project, 10,000 files, some very basic wrappers, some very basic convenience functions, and you get this kind of information that one of them failed, and it is used in 100 places. What you do? Start to cry, try to run your application and track the error, but you actually have no idea what data was provided there. You only know that the error fired from this line. But from this line, you cannot learn anything. You can only learn that there was something written to the config.js and the continuation function was wrong. So let us summarize callbacks. It's enough about callbacks already, right? There are some pros. Callbacks are very easy to use. I think you will agree with me. If you don't, raise your hand. Then it's very important that these tools are integrated by default in plenty of solutions. Loveit, Node.js, Boost Asio, Twisted in Python, and so on and so on. It's all over there, so it's low-hanging fruit. You have something to do, like you need to read a bunch of files, concatenate them, and go. This is a tool that is enough for this, but only this, and do not use it for anything else. The cons of these solutions unfortunately make it not worth recommending. Callbacks degrade to callback hell very quickly, and the code becomes unreadable, or on the other hand, the code structure and the logic flow of our application get disparate. So we cannot tell what our application does when we are reading the code. It doesn't help, certainly. Our stack traces will become unusable. In the simple example, if everything is anonymous Lambda function used in only one place, it works. But whenever we start to use some convenience wrapper, and we'll do sooner than later, we lose all the information, and we are actually doomed. So, last but not least, our callbacks are not addressing the complex flow control scenarios. We cannot do that. We need to do that manually. We need to handcraft solutions, and that is not increasing readability of our code. So what is the final statement about callbacks? Did they provide what we need or did they not? Did they pass our test or did they fail? If you think they passed our test, raise your hand now. Okay, there is nobody really in the whole room but here Michał, and I know Michał and I know he's joking. Yes, I agree with that. They failed to provide what we need. So now, let's move to promises, our next candidate for the solution of the problem. Promises are an abstract model of asynchronous computation results. It sounds very nice, very scientific, but promises actually boil down to this simple state chart. When you create a promise and bind an action, it's pending for the result. When the result comes and there were no other actions bound, it gets resolved, and this is final state. If you have bound more actions to this promise, it will then, on getting value, execute the next action related to the result it already got. It will pass that result to the next function, and it will go to the pending state again. In case of an error, if we have not provided an error handler, it will go to the rejected state. It means basically that we will never get the result because the computation couldn't have been fulfilled. But we can provide some kind of error or rejection handler, rejection callback. So when it goes to the rejection callback, it has the chance to resurrect our promise, to make it worthy again. For example, imagine that you are dealing with overloaded remote server, or you are dealing with unreliable transport network, and you want to communicate with the server across that network. Of course, it can happen then that the server doesn't respond in given time. Let it be 1 minute. So you set the rejection handler, and you write in that very rejection handler that in case timeout occurs, there is no response, but it is the very first timeout, you ask it to go back to the pending state, to do the recovery. And then if the conditions are not met, you are allowing it to get rejected, really, because we tried the recovery, it didn't help. So since we already know more or less what the promise is, let's see how it helps us, shall we? Do you remember this code? You didn't like it, I didn't like it. Can we do better with promises? Yes, we can. That very code, when using promises, becomes something like this. If you have just a tiny bit of imagination, you can imagine this code looking like this. So now, there is still some boilerplate, but our code structure and our business logic, they go exactly the same way as if they would do in synchronous code. And this is very important asset of promises. We have bound the logic and the code structure together again. So when you are reading the code, you know what it does, and when you know what the code is supposed to do, you know how the promises should be written. Then another case that we will be studying is the flow control. So we have two files, we want to read them. We create two different promises related to reading the file from the drive, and then we are asking our promise library to wait for all of them, and next, when both are fulfilled, to provide the results of both computations to next handler. This way we can build flow control, and we can wait for all or any of promises. So we can build any kind of flow control we want. We can combine them, we can select from them. This is more or less what the extended futures in C++ are supposed to provide in, hopefully, C++20. Yes, it's a bit of a joke. So then, What about call stacks? So far, so good. I like promises. They delivered so far what I wanted. Let's see, what about call stacks? We won't go through the very simple example without any convenience wrappers, because even callbacks were good enough then. We'll go with one convenience wrapper. It does really nothing. It just wraps one call in another call. Simple as that, but there is trap in that one. This is the very same issue as we had with our callbacks. Look at this. We have line number 8, where we are passing undefined as the name of the file that will be passed here. The line number 5. Line number 8, guilty. Line number 5, unguilty. Let's see. What have we got? Holy. There is a lot of noise, only from the promise library. And it says that the guilty line is the 5th one. There is, once again, nothing mentioning the line number 8 where the actual bug is. Would you accept that? I wouldn't. So let's summarize now. Promises, they have their pros. They provide better than callbacks, but the codes and the code structure and our business logic are now more coherent. They follow each other. They are tied together. They work together now. So this is very, very important asset. The readability of this code was just increased, and we should like it. I do. Then we have a means to provide the flow control. The promises provide good abstract model of the computation itself, so we can combine them, we can select from them, we can build flow control around them. There are unfortunately still some cons. There is still some boilerplate code needed for each and every code that we start. We need to call next, we need to schedule next promise, and so on and so on. It's not as bad as with callbacks, but still there is some. Our stack traces are once again not usable, and actually it got worse compared to callbacks. Somehow, promises provided worse than callbacks. It's not easy to be worse than callbacks, but promises did that, so miracle. So now, as with callbacks, we're deciding if they passed or failed our test. Do you think they passed our test? If they passed, raise your hand now. Okay, there is somebody there at the end. Only one person, 2 persons. There are 3 persons. There are 3 persons who like this. It is more than with callbacks, so that's good. This solution is better, but it's not good enough. So in my opinion, promises failed. The 3 persons who think they did well, let me introduce you to coroutines, okay? So, what a coroutine is. I think everybody here in this room knows what a thread is, and what operating system is, and what it does with a thread. But even then, I will very briefly tell. We have a thread, it executes some code, then operating system tells it to stop, suspend, it preempts it, it stays that very moment where it got preempted, and operating system starts or resumes another thread. Then it suspends the other thread, and it asks the first thread to continue. And it continues as if nothing happened. It even didn't notice it got suspended. It just continues. Coroutines are threads without operating system. Basically, there are threads that are cooperative. The coroutine itself tells when it wants to get suspended. And the other coroutine must tell that it wants to resume that very coroutine. We will use this very asset, this cooperativeness of coroutines, to build our solution around them. So we'll ask our coroutine to yield whenever it waits for asynchronous results. For example, our coroutine issues a call for reading a file. It yields immediately. It tells, I have nothing to do anymore. I am waiting for data from kernel. Do whatever else you like. I yield. And when the data becomes available on the queue, and our application decides it's ready to process the queue, it will resume our very coroutine with the data it was waiting for. Simple and beautiful as that. So our very first case related to the code, to the conversation, with coroutines becomes something like this. But do you remember the synchronous code? Is it really different now? Of course, there is some boilerplate here and here. We need to wrap our operation in a coroutine, but this code is exactly the same. So we got the code that is asynchronous, but it looks like the synchronous one. That's the holy grail of readability now. If we do it right, nobody will even notice there is asynchronicity going underneath. So this code does what the previous code did, but it reads as if it was synchronous. I don't know if we can do any better than this. Then the second example is flow control. We have seen that with promises it's possible to build it, and since coroutine itself is like a thread, the coroutine can also have different states. It can be executing, it can be finished, finalized, or not started. So we can wait for different coroutines, one of them, many of them, all of them, to finish the execution, and then only continue with another operation. So while with promises, we were setting up different promises, and then waiting for it to stop processing, to get resolved, with coroutines, we'll do other way around. We will have different operations, and we will split them amongst different coroutines, and we'll wait for the results to become available. But we can build flow control around it, and it is a great feature. And last but not least, debugging of our code. So once again, the messy example with the convenience wrapper somewhere that does actually nothing but the same what we did before. There is stat again over a function. It cannot work. We already know that it won't work. But let's look at this code closely now. There we have the back call. There we have the fstat over the function. So there is an error, but it's called here. And we have also coroutine wrap here and so on. The back function is called at line number 8. The actual back is in line number 4. What we get? We'll get all that information in our call stack. Since coroutines are threads, the call stack of the coroutine is never mangled in any way. When we execute the code with promises and we start the operation from the queue, we are building up new call stack. When we are operating with promise and we resume it, the call stack is resumed in the very same place. Coroutine is not noticing it got yielded and resumed. So we get all that information here, even there were different calls, asynchronous call in the meantime. We can see that there is one fstat here, here is another one, but it doesn't break our call stack. Even we did a synchronous operation in the middle, in the meantime. So what we got here is that there is an issue in the function bug. It was called from line number 8, and so on and so on. We got all that information, and we can exactly and precisely tell where the bug is and how we got there. So this time, we can actually tell how to fix this code looking only at that call stack. Finally. So let's sum up coroutines now. They resemble synchronous code, and it's the best we can get possibly. They provide abstraction of flow control, so as good as promises and better than our callbacks. They keep our stacks untouched. We get all the debugging information in case of a crash. We do not need to rely on some third-party solutions, some fancy logging and so on. We just get the information we want to get from the code. The stack is there for us. There are some cons. Actually, I see one. There is still some boilerplate needed. We still need to provide some additional code. We need to do some wrapping and so on. But it's neither for only for each flow of control. It's not needed for each call, as if with promises. It's needed only for the flow. So if you are building one conversation, we'll wrap the whole conversation now. So what's our verdict? Did coroutines provide what we need? If you think so, raise your hand now. I haven't convinced all of you, but more or less half of you. So good enough. I think you will change your mind when you actually try this. In my opinion, we cannot do better. And in my opinion, they succeeded. They passed our test. So, to sum up, too early, guys. So, to sum up, we have discussed callbacks, very simple and crude tools, promises, better, but callbacks, but coroutines were the best possible tools, and they only provide what we need. We shouldn't be using callbacks ever, unless we write the code for 5 to 20 lines. The promises only if we have to, if somebody forces us, and coroutines, this is something that we want to use. Coroutines are the holy grail of readable asynchronous code. It's time for Q&A. If you have any questions, please hit me.
So I have two questions, if I may. First one will be, what's your opinion on actor frameworks from, for example, Erlang or Elixir-like languages?
Actor and, for example, StageChart frameworks, they provide more or less on the same level as the promises do, because they are providing the flow control, they are providing quite good code readability, but unfortunately we are losing our stacks with them because they are not handling the stack anyhow. So if there is a queue, we'll only get the stack from that last moment we read the queue, and we'll lose the other flow. So they are more or less like promises, in my opinion.
Okay, and the second one is, have you heard of Boost Fibers in C++?
Boost Fibers is actually built on top of Boost Coroutines, and it is more or less what coroutine in Lua is. So yes, I have heard about it, and yes, that's a solution.
So do you think it's better than coroutines or not? Because the usage is like normal C++ thread, so
yes.
Each of us is aware of how it should work.
So coroutines and fibers, they are very similar ideas. Basically, the coroutines as implemented in Boost, they are not as flexible as, for example, coroutines that are supposed to be implemented in C++ itself or in Lua. And fibers fills that gap. So that is the very same solution. The fibers in Boost provide more syntactic sugar so that the code becomes more readable. But in general, the coroutines and fibers, in that context, this is the same solution, just wrapped in different way.
Yes, I have a question because I think there is some confusion about some conceptions that you used in your presentation, because the errors you shown is actually, the result of this error is just because you used a weak type languages in C++. It's a strong type language, so you would not even compile. So, I mean, the conclusion you drawn from showing the stack trace, you actually, I think, like a mixed two different things. One is from a concept how callbacks and promises works, and the second one is actually how the weak type and strong type language show errors and behave. And
okay, so then it means I provided even better than I thought, because I said there is no example in C++. This very example that you say it's strongly typed, it's not. It's Lua.
No, there is no any. Yeah, so that's the thing, that in C++ we would not see a problem with like a bug, because the program will not even compile.
Yes, of course.
I mean, in C++, you would not even compile the program, so you would see the bug immediately on the compile stage if you could write something.
If that would be the bug like this, yes, of course you are perfectly right. But these are not the only kinds of error. And if you would, for example, dereference null pointer, it would be exactly the same. You would get a stack that tells you nothing. So yes, it's harder to commit this kind of an issue in C++ because of static typing, or thanks to static typing, but it is still possible. And still, promises and callbacks will provide you very short stack trace related only to handling of this very result. And in case of coroutines, you will get the whole stack trace, how you got there. So even in C++, it works the same. It's just harder to commit this kind of issue.
Second question would be related actually to first slide. How do you count the zeros?
If there is an error, okay, I get it. If there is an error, it's not the point of this presentation. It's just an example how a readable or less readable code can look like. So we might not focus on this one at all. Okay. I take it. If you spotted an error, I believe you.
Okay, hi Kamil, I have a question. Okay, so it means we cannot employ coroutines in JavaScript?
In JavaScript, why? We can, of course we can do that. There is an effort in ECMAScript 6 to provide coroutines. They are already supported. Unfortunately, this is not a solution that the community of JavaScript is really happy about. But maybe with this presentation we can change it.
And what about some dedicated libraries?
Still, there are solutions. There are solutions for different languages like JavaScript. But the community, they are pretending that promises are better. For some reason, the community of JavaScript, of Node.js, chooses to use promises. Promises provide quite good handling. My point is coroutines are better. And if you are using Node.js on your daily basis, you should try it. Really, you should try it. It will, in my opinion, provide better for you.
A question about C++ coroutines. You mentioned C++ 20?
I don't know. I am not a member of the standard committee. But during the talk of Michael Wong, he already told that they are totally out of C++ 17. They are probably something that will be added in C++ 20, but it is, of course, subject to discussion of the committee.
If the exception is thrown in asynchronous code in C++, you probably see on the stack trace the event loop, and that's just the top of it.
Yes, but
do you know any tools to trace that exception more precise?
Yes, there are libraries related to stack traces. There is none in Boost, if I am not mistaken, but there are other libraries that you can use. Unfortunately, it means that any stack trace that is getting thrown by, for example, standard library, you will need to catch, rewrap with the stack trace information, and rethrow then. So unfortunately, C++ standard doesn't provide the stack trace with each and every exception, because then you would have to pay for something you might not use. But if you need that functionality, you can add it on top of the exceptions in your applications using third-party libraries.
You said that it's not possible to measure the readability of the code, but there are some types of the measurement, like you can measure, for example, intuitional, if the interface is intuitional, yeah? So you can also measure the type of the code. So maybe you can try to check how the the newbies, which are well-educated programmers, seeing at the first time the code, how they react. Yeah? Normally, if you check the readability of the interface, for example, it maybe looks funny, but it's just a counting of swear words, broken keyboards, harmed animals around, broken families, and so on. But I'm afraid that in such experiments with the code, we will have out of the scale results. So maybe this is the problem why we don't check this readability in practice. But of course you can check, you can measure it.
That's a
So this
very
is the
good
remark.
point. Yes, yes, that's a very good point. What I meant when I told that you cannot measure it, I meant you cannot measure it in synthetic way. You cannot do it with some tool. You need to have a group of people, do some behavior testing, check how they respond to the code. Yes, you can do that, of course. I basically had something different in mind. But if you would do behavioral testing, yes, it's possible. That's exactly what I did when I was asking what kind of code you like better.
Well, you can catch some bad code with Clang Tidy, for example, that will produce you even the fix it, how to make it better. It's still maybe only a syntactic sugar to the bad code, but it's still more readable bad code and easily to refactor then.
Yes, but right now it's addressing like very tiny bits of the code and doesn't get the whole picture, bigger picture in the scope. So it will tell you that, oh, here you can use unique pointer instead of auto pointer. It will do it for you, but that's more or less it. If it would have to compare if callbacks or coroutines are better, you would have the two different pieces of code doing the very same thing in one and other style. It cannot tell which one is better. It will only tell you that, okay, here you might have used different tool, but it's just very tiny information now. It is still artificial information that you provide to the tool. You are not really measuring how readable the code is. There was somebody with an idea in his mind that this library is better than that. So he hard-coded a check that if somebody uses this particular library with this particular call, you should suggest to the person to use the other. But it's not automated in any way. It's not measuring anything. It's just hard-coded logic.
Perhaps you could comment on memory and context switching profiles for the different solutions.
It really depends from one solution to the other. It depends. It differs between Lua and C++ and so on. So you would have to measure the very libraries you are going to use in the very environment you are using, very platform. But remember that the pre-measure optimization is the root of all evil. So as long as you have not measured it, and as long as you have not proven that it's using one or different solution, the root cause of your error, you should not optimize for memory or you should not optimize for CPU cycles. You shouldn't pessimize, but you shouldn't optimize either. So first do measurements and then go with it.
Okay, so I'd like to go ahead and thank Kamil for his very animated presentation. Please give him a round of applause.
Thank you very much.
As you can see, he's quite approachable, so you don't have to ask questions from the audience. You can come up and ask him directly. Better yet, ask him during the pre-party, party, and post-party. Buy him a beer, he'll tell you anything you want to know, okay?